When Lieutenant Colonel Peter Nissen trudged across the wet, freezing construction yards near Etaples in early 1916, architecture was the last thing on his mind. What he did think about, every single day, was how many British soldiers were dying simply because there was no proper shelter. The Western Front had chewed up not only men, but every traditional building method the British Army relied on. Timber was running out, carpenters were fighting in trenches instead of building huts, and every new structure needed to survive artillery that could land without warning. Nissen, a Canadian-born mining engineer serving with the Royal Engineers, had spent months watching a strange problem unfold. Stacks of corrugated iron sheets lay abandoned near supply depots, unused, because no one knew how to turn them into anything practical. Those curved metal panels were originally intended for roofing. Instead, they were gathering rust in the rain while men froze inside canvas tents that collapsed under snow. The brilliance of Nissen's solution wasn't sophistication. It was brutal, battlefield-grade simplicity. He took those same corrugated sheets and bent them into a half-cylinder. No internal framing. No complex joinery. A shape strong enough to stand on its own, and simple enough to build directly on bare ground. In March 1916, he assembled the first prototype at Etaples using nothing but standard-issue tools and 6 ordinary soldiers, men who had never built anything more complicated than a trench door. The hut rose in barely 4 hours. When Nissen presented his idea to British Army Command, he made one promise that changed military engineering forever. Any infantryman, using basic instructions, could erect the hut within 3 days, and all materials fit on a single lorry. The Army tested the concept immediately. At Richborough Port, the 172nd Tunnelling Company built 20 huts in April 1916. Each hut was 16 feet wide and required roughly 600 square feet of corrugated steel. The curved shape was a natural shield, rain, shrapnel, and debris slid off harmlessly instead of catching on vertical walls. By June 1916, Nissen huts were appearing across British positions from Flanders to the Somme. In August, the War Office placed its first massive order, 10,000 huts, all to be manufactured and shipped before winter. What made the Nissen hut revolutionary wasn't just speed, it was the complete removal of skilled labor. No carpenters. No masons. No engineers. The corrugated sheets arrived pre-drilled with holes exactly 14 inches apart. The wooden end walls came as prefabricated panels. Foundations were optional. Soldiers could bolt the hut directly onto wooden sleepers, or simply onto packed earth. A sergeant and 5 privates could unload the materials, lay the base, and have a weatherproof building standing before nightfall. During the Battle of the Somme in late 1916, construction teams built Nissen huts within artillery range, giving wounded soldiers immediate protection as they were evacuated from the front. The dimensions were optimized for wartime efficiency. 16 feet in width allowed 2 bunk rows with a central walkway, housing 30 men comfortably, or 50 in emergencies. The 15-foot roof arch allowed soldiers to stand upright. Adjustable vents on both ends provided airflow, and the steel's natural air gap prevented the condensation that plagued canvas tents. By the armistice of November 1918, the British military had deployed over 100,000 Nissen huts across Europe, Africa, and the Middle East. They served every purpose imaginable: barracks, medical stations, munition storage, command offices, instant infrastructure in a world collapsing into chaos. The technical brilliance lay in how Nissen redefined structural logic. Traditional military buildings relied on vertical posts, beams, trusses, components that demanded precision cutting and skilled assembly. Nissen abolished this entire framework. His curved corrugated sheets were both wall and roof, forming a single self-supporting shell. When one sheet overlapped another by 3 inches and was bolted through 3 layers of metal, the entire cylinder gained unified strength. Every bolt added structural integrity, not just coverage. The building sequence was foolproof by design. Lay wooden base plates in a rectangle. Bolt vertical wooden ribs at 7-foot intervals. Attach the first corrugated sheet, bolting it to the rib and base. Add sheet after sheet, overlapping tightly to form the half-cylinder. Install the pre-built end walls, complete with doors and windows. Experienced crews needed 72 hours. Raw recruits needed 4 to 5 days. The Army tested this repeatedly at training camps in Dover and Southampton throughout 1916. What truly separated the Nissen from later imitations was its ability to adapt to whatever materials were available. Nissen didn't design for perfection, he designed for reality. Britain's factories could roll 26-gauge corrugated steel without retooling. Bolts were the same 7/16" type used in naval construction, ensuring universal supply. Timber could be pine, oak, or salvaged from ruins. This adaptability made the hut nearly universal. In Mesopotamia, 1917, British troops built Nissen huts using brick end walls scavenged from destroyed villages. In Egypt, construction crews set huts directly on sand, propping interiors with palm tree posts instead of milled lumber. Yet the core principle remained unchanged. The curved corrugated steel created a weatherproof shell regardless of what surrounded it. At Vimy Ridge in March 1917, a Canadian unit built a Nissen hut during active bombardment, working in 30-minute intervals between artillery barrages. The hut went up in 18 hours and immediately sheltered 40 wounded soldiers. And logistics? The Nissen hut was unmatched. A single railway flat car could transport materials for 8 complete huts, 48 steel sheets, wooden components, and hardware. By 1917, British construction teams reached industrial levels of speed, completing one hut every 6 hours in rotating shifts. The Adaptables camp grew to house over 100,000 troops almost entirely in Nissen huts. The hospital section alone contained 300 huts, 12,000 beds. When the German Spring Offensive erupted in March 1918, engineers erected 70 additional hospital huts in just 11 days to shelter the wounded. The Nissen hut had become one of the fastest, most efficient military structures ever designed, an engineering revolution born not from abundance, but from desperation. By the time the British High Command fully realized the scale of the Western Front's logistical crisis in late 1916, the Nissen hut had already proven itself indispensable, but now the Army demanded something far greater. They needed entire cities built in weeks, not months. And they needed them in places where traditional construction would have been impossible: swampy fields in Flanders, shattered French villages reduced to rubble, and forward medical zones that shifted every few days. Nissen's design suddenly became the backbone of a massive wartime infrastructure program. At Adaptables, the Royal Engineers watched in disbelief as workshop crews and infantry details assembled 40, 50, even 60 huts a day. The construction yards looked like a steel forest, curved ribs rising in rows, men hauling sheets over their shoulders like shields, bolts clattering into buckets as if the entire camp was one giant machine working around the clock. What had started as an improvised shelter for small detachments had evolved into a standardized building system that could scale endlessly. But the real test came in the winter of 1916-17, the bitterest season many soldiers could remember. Canvas tents collapsed under wet snow, timber structures froze solid, and men in unlined wooden huts woke to find ice forming on the inside walls. Yet every Nissen hut remained dry, rigid, and standing. The curved steel shape shed snow naturally. The overlapping seams stopped wind infiltration. And charcoal stoves, installed near each end wall, heated the interior so efficiently that men often slept in shirt sleeves even when temperatures outside fell below -10 degrees Celsius. The War Office took note. In January 1917, they issued a directive. Nissen huts were now the official standard for all field accommodation across the British Expeditionary Force. This decision transformed military logistics overnight. Factories in Britain, Newcastle, Glasgow, Birmingham, converted entire production lines to corrugated steel rolling. Shipyards manufactured wooden frames and door panels. The British railway network assigned dedicated transport trains solely for Nissen hut components, nicknamed Tin Town Expresses. And with mass production came innovation. Engineers began modifying the design to suit every battlefield need imaginable. There were barrack huts with raised floors and triple-tier bunks. Field hospitals with expanded end sections for surgery tables. Signal huts wired for telegraph and phone systems. Ammunition depots reinforced with sandbag embankments. Officer mess halls with extended central spans. chapel huts, one of which famously hosted Easter service near Ypres. Mobile workshops for repairing rifles, machine guns, and even truck engines. A single concept had grown into an entire architectural ecosystem. Yet despite the exploding demand, the genius of the Nissen Hut remained its brutal practicality. Everything still had to be assembled by inexperienced soldiers. Most infantrymen had never held a spanner before joining the army. Some couldn't read detailed construction manuals. To solve this, the Royal Engineers rewrote the assembly instructions in the simplest possible language, short, direct, and nearly impossible to misunderstand. Bolt every hole you see. Tighten until washer cannot turn. Overlap sheets by 3 inches, no more, no less. These instructions were posted on wooden boards at building sites from Boulogne to Arras. Engineers even developed a rhythm for construction teams, 2 men on each sheet, 1 holding, 1 bolting. Another man passed fasteners. A sergeant paced the baseboards with a level and measuring stick. The entire process flowed like a drill, precise, repetitive, and surprisingly fast. By spring 1917, some engineer companies could erect a Nissen hut in 3 hours flat. Not a prototype. Not a demonstration. A full, operational building. What stunned observers most wasn't just the speed, it was the durability. German artillery routinely shelled rear area encampments, yet unless a shell landed a direct hit, the hut stayed intact. In fact, the curved roof often deflected blast waves upward, reducing structural damage compared to square wooden huts that shattered under concussive force. In forward zones, infantry battalions built miniature Nissen hut villages that became landmarks. Tin Alley at Passchendaele. Iron Crescent near Arras. The Blue Steel Camp outside Cambrai. Photographs from the time show endless rows of curved huts stretching to the horizon, each identical yet serving 1,000 different purposes. Meanwhile, Nissen's team continued refining the design. They standardized door frames, added ventilation covers, reinforced the wooden ribs with steel flanges, even created winter kits that included double-layer insulation panels made from felted wool sheets sandwiched between timber boards. The huts grew easier to transport, too. Earlier shipments required multiple wagons. By mid-1917, engineers packed an entire hut into a single compressed bundle, its parts nested like a metallic puzzle. This allowed uninterrupted supply flow even when rail lines were congested. A lorry could pull up to a mud-slicked field, unload the parts, and within hours a new structure stood ready: mess hall, barracks, supply store, or medical station. At the Battle of Arras, casualty clearing stations built from Nissen huts treated more than 5,000 wounded in just 9 days. Their arched interiors provided space for beds, equipment, and pathways for stretcher bearers, something no tent could match. They were dry, warm, easily lit, and quick to expand. By the summer of 1917, German prisoners who helped in construction commented, with some irritation, that British rear areas seemed to grow overnight. Every time the front shifted, new clusters of huts appeared like mushrooms after rain. The Germans relied on stone, timber, and heavy materials that demanded stable supply lines. The British used steel curves and portable bolts. This difference would play a significant role later, especially in rapid advances during the final months of the war. Perhaps the most surprising development was how quickly the huts became homes. Soldiers decorated them with chalk drawings, hung photographs, carved initials into wooden ends, even installed makeshift shelves from ammo crates. A small stove in the corner gave off a constant hum. Rain on the roof became a familiar sound, comforting, steady, and safe compared to the chaos outside. These weren't just shelters. They were islands of normality in a world collapsing into fire and mud. By late 1917, the British Army had constructed more than 45,000 Nissen huts, a number that continued to grow at a staggering rate. As vast and complex as the war had become, its infrastructure rested on a single idea: that soldiers deserved roofs that would not leak, walls that would not burn, and buildings that could rise wherever men needed to rest, heal, eat, or plan the next day's survival. The Nissen hut wasn't only an invention. It was a lifeline, simple, portable, nearly indestructible, and it followed the British Army wherever the war dragged it next. By 1918, the Nissen Hut had become an institution in itself. Military planners no longer thought of them as temporary shelters, they were a critical component of strategy. Supply depots, field hospitals, communication centers, and barracks relied on these simple steel shells. Entire divisions could now deploy with their own self-contained infrastructure, building entire camps in days rather than weeks. The speed and reliability of Nissen Huts allowed British forces to maintain momentum, especially during the 100 Days Offensive, where rapid advances demanded instant accommodation for men and material. The design's flexibility proved invaluable. At the front in Flanders, engineers adapted huts to uneven terrain by adjusting bay sleepers or stacking sandbags along one side. In the deserts of Mesopotamia, wooden end walls were sometimes replaced by mud bricks to keep interiors cooler. Even in cold northern climates, crews layered additional timber or canvas inside for insulation. No matter the location, the core principle remained the same: curved corrugated steel could provide a self-supporting, weatherproof shell with minimal tools and training. The ingenuity of Nissen's approach contrasted sharply with later American efforts. By the time the United States entered World War II, engineers had examined British methods carefully. Commander George Dorrit's report on the Nissen Hut had highlighted the simplicity and speed advantages of the design. But when American engineers at Quonset Point began developing their own version, they prioritized permanence and comfort over speed. The Quonset Hut introduced an internal steel frame, insulation, and electrical systems, creating a structure that was more complex, heavier, and slower to assemble. Testing confirmed the trade-offs. A fully assembled Quonset Hut required at least 96 hours with trained crews, while a Nissen Hut could be built in 48 to 54 hours by the same team. Electrical systems, interior insulation, and framework alignment consumed valuable time, luxuries that forward combat zones often couldn't afford. When deployed in remote or hostile environments, Quonset construction delays sometimes left troops exposed to weather and enemy fire, a problem Nissen had solved with ruthless efficiency decades earlier. The Pacific Theater illustrated these differences vividly. On Guadalcanal, Marines struggled with Quonset huts under extreme heat and humidity. Steel ribs became too hot to handle safely, insulation layers were difficult to install in the field, and electrical wiring had to be carefully coordinated with construction crews. Meanwhile, Australian engineers working with Nissen-style huts could assemble shelters in 36 hours, often without wooden end walls, using only locally sourced timber and corrugated sheets. In practice, speed often mattered far more than comfort. Field reports consistently reinforced the lesson: in combat, speed trumps perfection. During the expansion of Fufuti Atoll in March 1943, engineers measured exact assembly times under identical conditions. Nissen-style huts averaged 54 hours from first base to completed structure. Quonset huts averaged 91 hours, with delays arising primarily from framework alignment, insulation installation, and interior finishes. In forward deployments, those 37 extra hours could mean the difference between life and death for soldiers in the mud or under bombardment. Logistics also favored Nissen designs. Entire Nissen huts could be transported in compact bundles, carried on a single railway flat car, and erected with minimal manpower. Quonset huts required specialized transport for heavier components, including steel ribs, insulation panels, and interior plywood, introducing more potential points of failure during shipping. In wartime, every hour and every ton mattered. By mid-1943, American production reached staggering volumes. Factories in Indiana and Pennsylvania produced thousands of Quonset huts monthly. The Strand Steel Corporation alone was assembling 200 units per day. Standardization ensured that components from January 1943 fit perfectly with parts manufactured in August 1944, but this came at the cost of flexibility. A single missing or damaged rib could delay entire installations, whereas Nissen huts tolerated minor imperfections and improvised adjustments in the field. Cost differences were stark. A 40-foot Nissen Hut cost roughly $230 in inflation-adjusted $1,943. The American Quonset, with its insulation, electrical systems, and internal framework, cost $850, a nearly 300% increase. Over thousands of units, the expense multiplied rapidly. Yet the American approach emphasized permanence, functionality, and modular interior systems, while the Nissen design prioritized speed, adaptability, and field repairability. Perhaps the most enduring legacy of the Nissen hut was its versatility. Soldiers could disassemble huts quickly and reuse the components in new locations. British engineers routinely relocated entire Nissen hut camps from Egypt to Italy, or from Greece to France, as front lines shifted. Quonset huts, tied to their internal steel frames, could not be dismantled and transported with the same ease. Once assembled, they were largely permanent. This difference highlighted a fundamental design philosophy. Nissen huts were meant to follow the army wherever it moved, Quonsets were meant to stay put, comfortable but immobile. After World War II, these philosophies manifested in civilian life. The United States sold surplus Quonsets to farmers, small businesses, and families at prices between $200 and $600. Their integrated floors, insulation, and electrical wiring made them immediately habitable, leading to decades-long civilian use. Meanwhile, Britain dismantled most Nissen huts, often recycling the corrugated steel during post-war shortages. Only a handful survived, primarily on farms or military ranges, as historical relics rather than functional buildings. Architectural critics largely ignored both designs or derided them as crude. Frank Lloyd Wright reportedly dismissed Quonsets as metal pig shelters, while British architects called Nissen huts corrugated embarrassments. Yet millions of soldiers owed their survival, health, and comfort to these simple structures. Practicality and performance outweighed aesthetics, a principle often lost on critics but never forgotten by those who lived in them. Both designs left lasting lessons for military engineering. Simplicity enables speed. Durability requires understanding environmental conditions. Adaptability is as valuable as comfort. From World War I to the Pacific campaigns of World War II, the tension between minimalism and sophistication defined shelter logistics. The Nissen hut was a triumph of minimalism, the Quonset hut was a triumph of engineered comfort. Each reflected the priorities and industrial capacities of their respective nations. The post-war trajectories of Nissen and Quonset huts illustrate the contrast between military necessity and industrial ambition. Nissen huts, conceived in the mud and shellfire of the Western Front, exemplified ruthless efficiency, minimal materials, minimal labor, maximum speed. They could be built under artillery fire by soldiers with no construction training, adapted to almost any environment, and relocated as battles shifted. Their simplicity made them nearly indestructible in practical terms, though aesthetically unremarkable. In contrast, Quonset huts embodied the American philosophy of engineered permanence, insulated, electrically equipped, structurally reinforced, and suitable for long-term occupation. They were heavier, slower to build, and more complex to deploy, yet offered comfort and adaptability for semi-permanent bases. Civilian adoption highlighted the philosophical divide. In the United States, surplus Quonsets became machinery sheds, family homes, workshops, and even temporary student housing. Many survived for decades because their integrated floors, insulation, and steel framework made them highly durable. Across rural America, they became iconic symbols of post-war pragmatism, repurposed with minimal modification but providing maximum utility. Britain, however, largely dismantled Nissen huts, recycling steel and timber during post-war austerity. Only a few remained, tucked away on farms or military properties, their survival owed to practicality rather than planning. The ephemeral nature of Nissen huts mirrored their battlefield intent, shelter where and when it was needed, then abandoned without regret once the front moved on. Modern construction and military doctrine continue to echo lessons first demonstrated by these early prefabricated shelters. Expeditionary and rapid deployment units increasingly prioritize modular, lightweight, and quickly assembled structures, essentially a return to Nissen's core principle of speed over perfection. Military engineers in Iraq, Afghanistan, and other rapid deployment scenarios recognized that infrastructure cannot always wait for ideal conditions, a concept codified in the U.S. Marine Corps Expeditionary Advanced Base Operations in 2019. The essential question remains unchanged: how can soldiers, engineers, or disaster responders create habitable, functional structures in the shortest time with available resources? The broader implications extend beyond the military. Disaster relief, emergency housing, and humanitarian operations frequently grapple with the same trade-offs. After Hurricane Katrina in 2005, FEMA's temporary housing initiatives demonstrated the limitations of over-engineered solutions. Prefab homes requiring concrete foundations and utility hookups delayed occupancy for weeks. A Nissen-inspired approach, simple, transportable, and rapidly deployable, could have provided immediate shelter while permanent reconstruction proceeded, saving countless lives and resources. The enduring lesson of the Nissen versus Quonset comparison is philosophical as much as technical. Peter Nissen asked a deceptively simple question: what is the absolute minimum required to keep soldiers dry and alive? His answer: curved corrugated metal, bolted together, no foundations, no internal framing, prioritized utility above all else. American engineers, confronted with the same problem decades later, asked a different question: how can we make it better, stronger, more comfortable? Their answer: internal frameworks, insulation, electrical systems, produce superior buildings by many measures but sacrificed the one element that mattered most in urgent, mobile warfare: speed. In the end, efficiency and sufficiency often outperformed excellence when time and conditions were critical. From a technical perspective, the Nissen Hut's brilliance lay in its minimalist engineering. Each corrugated sheet was simultaneously wall and roof, bearing structural loads while allowing overlap for integrity. Prefabricated components minimized skill requirements and field improvisation. Quonset Huts, by contrast, introduced dependencies, precisely bent steel ribs, exact alignment, integrated interior systems, all requiring trained labor, tools, and careful site preparation. The choice between them reflected national priorities and industrial capability, British expedience versus American permanence. Architectural historians and military engineers continue to study these designs, extracting insights relevant to modern challenges. Modular container shelters, rapidly deployable expeditionary bases, and emergency disaster relief housing draw directly from the Nissen principle of functional simplicity. Industrialized prefabricated housing, corporate campuses, and even modular civilian projects echo Quonset-style engineering, emphasizing comfort, durability, and standardization. The tension between speed and perfection, temporary versus permanent, simplicity versus complexity, remains central to design, logistics, and operational planning. Ultimately, the Nissen Hut stands as a monument to necessity-driven innovation. Its lasting lesson is not just about metal and bolts, but about asking the right question under constraints: what is truly essential? The Quonset Hut, conversely, embodies the virtues and limitations of engineered perfection. Both changed the lives of millions of soldiers and civilians, and both left a tangible architectural legacy. Across battlefields, farms, and training grounds, surviving structures continue to illustrate the profound impact of design philosophy on human experience. The final takeaway is clear: innovation is not inherently measured by technological sophistication, but by appropriateness to context. In combat, as in disaster zones or rapid deployments, speed, simplicity, and adaptability often outweigh comfort, permanence, or aesthetic refinement. The Nissen versus Quonset story is a study in priorities, revealing that engineering solutions are only as valuable as the problems they solve, and sometimes, the simplest solution is the most profound.